we're introducing this new G-vectoring control technology that is a very subtle, but we think very important thing. And it's so subtle that when I first learned of it, I was told how it works and given a car and said, "Here, go check it out," and I couldn't even feel it. I didn't know, because I was looking in the wrong place. If you think about how it works, you look for the wrong thing, so we put together an annoyingly structured day that just bear with us through the amount of just go exactly this speed, do exactly this thing. I know that's annoying, but we did that because it makes it so much easier to feel what this does. And once you recognize that feeling and can attribute it to this technology, then you'll be able to feel it anywhere when you drive. You guys are the only ones, anybody who's comes to one of these programs will be the only ones who ever have an on-off switch to feel GVC by itself. When we put it in production, it'll just be part of the car. There won't be any way to turn it off. So it'll just be part of why the car drives well. We walk you through a very structured set of driving exercises simply to make it a lot easier for you to get what we're talking about. So have patience with it, that's all. In order to understand what this is and why we did it, we first have to step back and look at philosophy about what. You know how Mazdas drive, but I think we need to back up into sort of the headspace of Mazda and why we do what we do, why we make the cars this way. Because we have cars that speak to enthusiasts, built by enthusiasts, but in order to make a business case for that, and in order to make something that actually works in a broader sense than just the few of us that still care about driving cars, you've got to have sort of a deeper sense of why that matters. And so part of this philosophy lessons will be a language lesson of the five Japanese words that I know. Doesn't matter if you learn the 5 words, it matters if you learn what they mean and what they're all about. So Hashiro Yorikobi is sort of the overarching philosophy behind Mazda. And what this poorly translates to is fun to drive or joy of driving. More sort of closely, it's more the joy from driving, which is a subtly different thing. If you really kind of take it in context, it is the fundamental joy of being moved faster than you should be able to be moved. Consider that you are a very smart monkey and you should be able to run around on your little monkey feet, and that should be your performance envelope. And the fact that you can get into this machine and go faster and do more than your little monkey feet should be able to do, that is a fundamentally joyful thing at very root of your brain, right? At the same time, at the very root of the brain, there is a part of you that is absolutely terrified by the exact same fact, because you weren't designed to do this, right? And whether you feel that joy or that terror comes down to how well you feel like you're in control of the car. And so there's 2 sort of key things that come out of this goal to striving for this Hashiro Yorikobi in all of our cars. One is that concept is not something that speaks only to enthusiasts. As a human, you can enjoy driving. That's the point. The other thing is that we have to make the cars so predictable and so controllable and so intuitive that you never feel that fear, that you only feel the joy. So that's what that philosophy is all about, and that's why we sweat the details that we sweat. You guys can probably tell me what Jin by time means. I don't have to explain that. We've been yapping about this for a long time. But the basic concept comes from the ancient Japanese horse archery called yabusami, which is the 5th word. Yabusami is when they've got a horse galloping, an archer on the back of a horse galloping at like 25 miles an hour, and the guy's standing up on the horse and shooting at a target as he goes by. The relationship that horse and that rider have to have in order to pull off that very precise, high-speed, coordinated action is the relationship that we're going for in the car. The rider knows exactly what the horse is going to do, has a very consistent stride. He knows exactly when in that stride it's going to be stable enough for him to shoot his arrow. The horse is responding to very subtle inputs from the rider through his legs and through his knees. Or so I'm told. I can't even ride a horse. But conceptually, it's the way that those two can communicate through very subtle, detailed things, and the relationship that they have, and the fact that if you have this really intimate relationship with the thing that you're controlling, you will form an emotional bond with it. And at its root, what we're trying to do, if we get the car to drive right, if we get the driver to feel this Jin-by-Tai feeling with the car, they form an emotional bond with that car, which on its surface sounds silly and ridiculous, but ask anyone who's driven a Miata or who has owned a Miata, and they have an emotional bond with their car. So it's possible. That's why we try to bake so much Miata into every car we make. Ultimately, you make a car that any human can appreciate the joy of getting in and moving in it, and you make it so good that they love that car, they'll come back. That is the high-minded hope that we have, and why we bother to do stuff like this. Just to drive home the point that this Jin-by-Tai thing is not a new program. That's a 25-year-old quote talking about the oneness between man and horse. We weren't actually using the Japanese at that point, but that was. I think that imagery of the Yabusame was started being used in our development of the first Miata. I think the concept of what we were trying to do, it goes back even farther than that. If you drive an old first-gen RX-7, if you're lucky enough to get behind the wheel of an original Cosmo, we've been doing that same thing forever, but we've been slowly over the years trying to make it more consistent and get better at it. And in that vein, with the SkyTube generation of cars, we've really started to kind of try to formalize and dig deeper into how exactly do we get this Jin-by-Tai feeling in a car. Since you judge that by the seat of your pants and how it feels when you drive the car, a lot of our tuning ends up being seat of the pants. But there's an inconsistency that comes with tuning from the seat of your pants, and we want to try to really dig deeper and get down to what is fundamentally driving that feeling of connectedness with a car, so we can understand it better, so that we can engineer to it more consistently and more precisely. And so to do that, we've been studying humans, because to make something intuitive to a human, you have to understand humans and what would be intuitive to them. So you have to kind of dig deep to some fundamental truth and build up from that. And there's still plenty of seat of the pants flavor that we can get on the way from that to the final car. But if you build it up on a foundation of fundamentals, I think you get to a much better result. And what I'm going to talk about here is part of sort of what has contributed to that huge leap you saw when the SkyTube generation of cars came out, and how much better they were than our previous generation of cars. A lot of this stuff happened around then. So there's two kind of overarching concepts in our human studies that have driven a lot of our development. One is minimum jerk theory, which is a study of how humans move, and generally how mammals move, really. And it's not something we had to figure out. There's lots of human physiology studies and lots of robotic studies trying to study human physiology to make the robots seem more natural, so they can take over and be our overlords. And minimum jerk theory is something that stems out of that. Equilibrioception is this sort of subroutine going on in the root of your brain to help you stabilize yourself. This is how you recognize G-forces, and making G-forces intuitive to the people in the car is sort of key to making the car feel right. So understanding how the equilibrioception works is really important. So to understand minimum jerk theory, you first have to understand exactly what we mean by jerk. Jerk is the technical term. It's for the rate of change of acceleration, right? So if you think about what velocity and acceleration and jerk mean to the human body, think about when you're riding a train, standing in a train. Velocity is meaningless to you in that train. It's just the blur out the window. You don't actually feel it. As a sensation, there's no sensation of velocity. Acceleration you feel, but of a constant acceleration, you can just lean into it and cancel it out, and you deal with that very easily. Jerk, the rate of change of acceleration, that is what will knock you on your ass when you're trying to stand on a train, right? If that acceleration changes in an unexpected way, you won't be able to compensate for it properly, and you'll fall over. So it's jerk that is the element that we need to look closely at when discussing how a car responds. And minimum jerk theory is just the it's not so much a theory as an observation that when people move, they always do it in a way that has the lowest jerk. If I just pick up this bottle and move it over here, without any thought at all, I happen to accelerate it and decelerate it in the smoothest way possible with the lowest jerk possible. And the only reason I did that is because that's the lowest energy way to do it. And therefore, I'm going to eat a little bit less than somebody who's a little jerkier, and then I'm going to have a better chance of living on and procreating. And there we go. Now we have evolution. So this is why mammals do this. It just happened to work. We can actually instrument people and observe this minimum jerk. If you put the electromyogram thingamabobs, the sensors, the voltage sensors you can put on your muscles and get a reading off of. If you put that on a muscle, the voltage input to a muscle is directly proportional to the force output of that muscle. The force output of that muscle is directly proportional to the acceleration of that muscle. So we watch the profile of the acceleration spike in someone's muscle, you can see how they're accelerating that body part. So if you look at someone's stride here, for example, and you look at the calf muscle output on every stride, you see it has that nice bell-shaped curve. That is the profile you'll see in a minimum jerk output. So that we look for that sort of bell-shaped curve and see it everywhere in natural motion, and then end up using that as our target for a lot of the ways the car behaves. The other element, equilibrioception, is oversimplified, just the fact that people like to keep their heads upright. No matter what they're doing, as they're balancing themselves, their head's always upright. We kind of take the output of that deep-rooted subroutine that is balancing our head as our sensor to tell us how much G-forces we're feeling. So in a sense, the seat of your pants is actually in your neck. This is how you're sensing G-forces. If you're driving a car and you feel how it accelerates, and the car stumbles or hesitates, your neck shoots forward because you were anticipating a certain acceleration from that, and your neck is countering that G-force. And when you miss, you do the pigeon thing. Speaking of pigeons, this is a very deep-rooted process. It's nothing special to humans. We're actually not nearly as good at it as chickens are, as it turns out. But this is, I put this up here to illustrate just how completely subconscious this is. This is way down in your chicken brain, right? But as we understand it, it's the output of this process that tells us what's going on. So if we take what we know about the way people move and the way they expect their body to move and the way that we're sensing those forces, you realize that there's a connection between your calf muscle and your neck muscle that is deeply hardwired. When you walk, every stride you make, you're pushing off with your calf muscle. That's accelerating your body, and your neck is countering that to keep your head balanced on top of your shoulders, right? And so there is a deep-seated expectation when you make a calf input of what that output should be. And so going off this observation, it seems that when we make sort of this normal bell-shaped minimum jerk input, we should be expecting a normal bell-shaped output. That's the acceleration we put into our body, and that's what we counter with our neck. And there's no delay, there's no throttle lag in our stride. So based on that theory, we then went back and started instrumenting some cars that we thought had really great natural throttle response to see if they were doing what we thought we were doing. If you look at a 997, we've got the squiggly one in the middle there is the calf muscle output as we're in third gear, cruising along, and just tip into about 50% more throttle than we had at cruise. Your normal input speed is a normal bell curve minimum jerk input. You can see the gas pedal input speed follows that same curve as the voltage, because that's how muscles work. And the acceleration jerk, the rate of change of acceleration, ramps up and down in this smooth bell-shaped fashion, just like we expected. And the lag here in the 911 is about 250 milliseconds. 200 to 250 milliseconds is the minimum you can recognize in a time lag. So they're right on, getting it to almost imperceptible time lag, and they have exactly the output that we thought that it should. So this is what we were shooting for with the with all of our cars. So the 2.5 Mazda 3. This is on a different scale, unfortunately. So that time lag looks huge. It's actually 300 milliseconds. So just a hair longer than the Porsche. Obviously, the G isn't nearly as high as the 911, but the way it's delivered is exactly what our brain is expecting, and that's why that throttle response feels so natural. No point makes any sense without a counterpoint. So here's what an FRS does when you give it the similar input. It's almost a 500 millisecond lag, and then the actual acceleration itself is jerky, which is a nice alignment of technical term and real term. A GTI is a sort of, even though it's a quite good turbo engine, it still has a very typically turbo output. So not too much lag for the initial response, but you have a two-step response where the engine naturally aspirated has one response, and then after a little while, it comes up and has a turbo response. And while that big surge in G is exciting, it is exciting as a passenger, and you as a driver are then a passenger because it does nothing to do with your input. And what I've always noticed when you're driving a car that has a really direct connected throttle response versus one that doesn't, and some cars will behave one way at some times and another way at other times, so you can feel this happen in the same car. When it gives you that direct throttle response that you're expecting, the gas pedal feels different. It feels firmer and it feels like it's connected to something. Whereas as soon as it doesn't do what you expect it to do, you just feel like you're pushing on this springy thing that just feels squishy. And obviously the pedal itself is the same thing, but the way your brain is processing what that is completely different. So this is just giving you that sort of squishy, the nothing pedal until it wakes up and gives you the response you want. The other area that we studied is the way your head moves as you're walking and how this can relate to how we can tune our suspension to make the car ride better. If you're walking along straight, your sense is that you're just walking straight. The reality is your head, where all your senses mostly come from, is bobbing up and down and weaving side to side, and you're automatically filtering this out of your sense of your sense of motion. So it turns out we have some filter mechanism going all the time to filter that out if the motion is like that, like what we expect. You notice that motion has that same smooth sinusoidal kind of minimum jerk motion. We took this and went again and looked at some cars that we thought had a really good balance of firm, controllable ride and good ride comfort at the same time, which is something that we struggled with for a long time because we always want our cars to really feel connected and planted and responsive, and yet that tends to make a car stiff and harsh and ride poorly. And you know, back in the 90s and early 2000s when BMW was really good at doing this stuff, we went and measured their cars, and sure enough, they were moving around a lot more than it felt like they were. But they were doing it in this same sinusoidal minimum jerk way, and they were doing it where the front and rear are matched. When you walk, there's no pitching. Your head's not going forward and back like this, but it is bobbing up and down and moving side to side. So we can accept this motion in a car and filter it out and still feel connected to the road, as long as it's not pitching and as long as that motion is damped in that minimum jerk manner, so it doesn't have any kind of peakiness to the motion, and as long as it damps out quickly enough that you don't end up feeling like you're in a Buick. But old Buick, I've driven a recent one, so nothing personal if anybody likes the new Buicks. But this really kind of helped us find a better ride handling balance in looking at what people are going to naturally filter out. The other area that's much more sort of complicated is our steering and handling response and trying to figure out how to make that feel right, because steering and handling there's a lot of different motions and forces in a lot of different directions all being coordinated at the same time, and this gets much more tricky to figure out what feels natural. So I can't necessarily point to a single element of the way humans move and say, look, this is all we needed to do. But there's sort of three key things that we've started doing with this generation of car that really seems to pay off in making the car feel natural. One is we have a lot more steering feedback. The you need to have a direct correlation between the amount of force you're putting into the wheel and the amount of cornering force that the car is going to generate. And in sensing that through your hands lets you give exactly the right input to get the output you want. There's a little bit of phase lag from the input to the actual vehicle response through rubber tires and bushings and such. But since you can feel that faster through your hands than you can in waiting for the forces to get to you, this makes you give better inputs and makes you a better driver. The other kind of surprisingly subtle thing that we figured out is that if the car has the initial roll posture, when you first make a little bit of an input, if it's diagonal, so the outside front corner drops before the car goes into the corner, that seems to help for a couple of different reasons. One reason we think is that when you're walking, anytime you turn when you're walking, if you think about how you make yourself turn, you always have to turn on a downstroke with your outside foot. Like, I'm not going to turn like this with my inside foot. The force doesn't work that way. I've got to push with an outside foot, and since you've got to do it when that foot's out in front of you, that means there is always a downstroke, a little bit of deceleration because your foot's out in front as you're pushing off, and so you've got this sort of three-dimensional profile to the way the force arrives in your body. And the other thing, the reason we think this helps is that in having to balance yourself against these lateral forces, which is not something that humans are really made for. We don't have a lot of lateral forces in nature. Because when we run around a corner, we lean into it like a motorcycle, right? So you're not really dealing with much lateral G. But this visually seeing this diagonal roll before the forces arrive prepares you subconsciously for that G-force, and so it doesn't surprise you. So everything feels smoother and more natural. So that's part of why all of our cars now have longer hoods that you can actually see from the driver's seat. The design guys really like that for their own reasons, but the engineering guys were completely on board, and there always has to sort of be this agreement between those two teams. And so this is a nice area where everyone was on board with long hoods and more upright A-pillars, so we could see that stuff better. And the final sort of element of steering handling tuning is coordinating the roll and lateral G and yaw motions. So all these things are coming at you at the same time, and a lot of cars actually don't coordinate them very well. What we found is that you want the initial roll motion to happen just a fraction of a second before anything else has that warning sign, but then the lateral G and the yaw motion need to be coordinated and need to start up together. You'll notice some cars that feel a little nervous and tail happy and in some ways sporty and fun. When you turn into a corner, they'll kind of rotate a little bit, and then they'll hook up and go. And that can be entertaining, but it can also be scary for some people. It is an unnatural thing to have this rotation come out of nowhere. And eventually you'll learn to maybe trust that this rotation means it's going to do that if you're one of us who's very aware of driving and what to do with it. If you're a normal human, you'll probably just be scared all the time. But coordinating those so all of it happens together just makes the car fundamentally feel natural, and it just blends into the background and becomes just a normal thing. And that's really key to making the car's behavior be so normal that you don't think about it. It's just like doing that. I didn't think about how I accelerated that. It just worked. So we started trying to incorporate those elements as much as possible when we did the second generation Mazda 5. So this was just before the Skytip generation of cars were ready. But this was a good case study because this was two cars that were exactly the same platform, almost exactly the same powertrain, just some new sheet metal and some new tuning. So it's a sort of a good A to B comparison. And what we're trying to do is make it so that G vector as you go into a corner, you get the braking, the smooth transition, the cornering, just like as you're walking around a corner. And we want to make it a lot easier for you to make that transition as you brake into a corner and make that initial input so that is one smooth motion rather than being a braking input and a cornering input. And you can see on these G plots that's sort of representing the way the turn-in was on this on the old car was very sharp and very nimble and fun in a lot of ways, but it wasn't that easy to control exactly when that lateral jerk arrived. And so you'd have this very sort of distinct braking area and then sort of a recovery and a very abrupt transition into turn-in. whereas the new car is much smoother and easier to fill out that sort of that transition around turn-in. That shows that we got our G-vectoring moving around. It doesn't necessarily show whether it matters or not. To see whether it mattered, we actually instrumented the passenger's neck to watch how they're responding to that input. And you see in the old car this sudden spike in muscle voltage there. That indicates that they didn't see that lateral jerk coming. And what happens, their head started to fall off to the side and they had to snatch it, catch it, and bring it back up. That, you never see that kind of muscle input in an intentional, normal human motion. With the newer tuning, we have this normal kind of minimum jerk, smooth ramp up in muscle voltage. That indicated to us that it's making the car more comfortable and more easier, more sort of natural for the people inside of it. If charts and graphs aren't convincing, then a model in the passenger seat's always more convincing. We hired a local modeling agency near Hiroshima, near a test track, and told this girl to sit in the car and smile, and didn't really tell her why. And drove around the same corner at the same speed, same ultimate cornering Gs, as you can see on a very bad day. So the cornering Gs are not very high. This is just absolutely normal driving. And this was in the old Mazda 3 versus the current one. And you can see the difference in how much she's moving around in the seat with the same corner and the same speed. And the difference is in the way those cornering forces are arriving and how well she's able to anticipate them and brace for them completely subconsciously. Some differences in the seat being perhaps a little bit more supportive as well, but it's not like we just discovered making supportive seats in this generation. We've been pretty good at that for a while. So this I think really illustrates in a more understandable way how that pays off in the car. So we're breaking this presentation thing up into two pieces. First, just sort of this sort of philosophical background and what it is we're doing overall. We're going to go out and drive annoyingly slow in a little circle in a couple of cars. This is an exercise we've been doing a lot internally with a lot of Mazda employees to try to get them focused in on these details as well. And this driving exercise really just helps you focus in on the really small, precise details that we're working on the cars. We'll drive a CX-5 and a Forester and a CR-V at 5 miles an hour and 10 miles an hour. And this takes out all of the noise and all the stuff that's going on in normal driving and lets you just focus on really precisely how well does the car respond and how precisely does it respond, how easy is it to control these very subtle things. After that, we'll jump out and get into a Mazda 6 that's got the GVC switch that we can turn on and off. And we'll drive in this very simple course that makes it easy to kind of pinpoint exactly what it is that it's doing that's different. Then we'll come back in here and I'll explain what it actually is, because it doesn't seem like what it is would do what you felt. And then after lunch, we'll go back out and we've got a bunch of other exercises to kind of feel it in more different environments. And then finally, we'll just go out on the road and drive it for real like a normal human. So this is something that came out of studying drivers again and looking at how really good drivers use weight transfer to make the car drive better, more consistently. We started by looking at people who are left foot braking or just lift throttle at turn in and trying to figure out how to automate what they're doing and build it into the way the car responds. So initially we started off trying to actually duplicate it using the brake system. So every time you turn in, it would use a little bit of brake and sharpen the response. But the brake system doesn't work fast enough. So ultimately, what this system is conceptually really, really simple. Every time you make a steering wheel input, it reduces the engine torque a ridiculously small amount, enough to shift a little bit of extra load onto the front tires, and that extra load on the front tires sharpens the response and gives a better feedback and gives a more natural cornering posture. There's basically two different things going on when you do that. One is the way it's changing the way the tire responds. Part of that is just friction. If I slide something across the table and I put a load on it, it's harder to slide across the table. So the more vertical load you put on the table, the more grip you have. That part of it really shows up when you're on snow or ice. The other part is it certainly tightens up the carcass when you load the tire up, so it takes less of a slip angle to generate the same amount of cornering force. But the other thing it's doing is it's that little bit of reduction in torque, shifting weight to the front of the car, makes the nose start to dive a little bit, and it starts that diagonal roll process where we're trying to get that three-dimensional motion that matches the way people turn on their feet. And that, again, just subtly feels more natural. And one of the biggest challenges to getting this very small, very subtle diagonal roll that we're always working on is we want it to happen right at the very smallest steering input. And to do that, you have to overcome the stiction in the suspension. And so, we go ahead and spend the extra dollars on the lower friction bushings in the struts, and so they'll move a little bit more easily. But this little trick also really helps get them moving and get them unstuck, and get the suspension motion to work better in a corner.
Sorry.
Yeah.
So you said small steering inputs, you're talking like changing lanes on the highway. It's doing this.
Any steering input, we're looking at the steering wheel velocity, and the steering electric power steering system reads 1/10 of a degree of steering input.
Yep.
So it can respond to that small of a steering input, and the amount of torque reduction that it does to shift weight is proportional to your steering speed and your vehicle speed and how much throttle you have, but the absolute most weight transfer it can do, the absolute most G reduction that it can do is 0.05 G, which is less than you can feel, which is why we didn't want to explain what it does before you felt it, because it was explained to us, and when I went out there driving trying to feel the G reduction, trying to feel what it was doing to the engine, you can't feel that. All you can feel is the results. And the result of that tighter carcass is actually in the steering. You feel more buildup right around center, but sort of more importantly, you feel more consistency, more directness in the response. Back to the sort of process of when we were developing this. Umetsu-san here, sitting behind you guys, he worked on this for 8 years, trying to get it to work right. Initially, we chased down the brake path, and the amount of time lag between when we sent the brake system a signals to give us a little bit of negative G to it moving the fluid, moving the pads, and actually giving something was too long. Like I said, you can consciously notice 200 milliseconds. You can sort of unconsciously notice something is wrong, down around 100 milliseconds. And the brake simply couldn't respond quickly enough for that. At the time, even our powertrains couldn't. So even if we sent a torque reduction signal to the engine, the engine control processors were too slow with the old MZR engines, and we couldn't even control that fast enough. So trying to figure out how to get this to work was actually done on a Mazda Demio EV, because an electric motor can respond to exactly what we tell it to do. And it wasn't until the SkyActiv engines were available and the faster computers that we've got running those and the faster communication that we've got on the CAN bus in the car to get the information from the steering system into the PCM that we could actually get the response that's fast enough to make this work. Oops, I'm going the wrong way. Again, conceptually, all we're doing is the amount that we're reducing the torque is just a function of lateral jerk is directly proportional to steering wheel speed. So we actually take, instead of waiting for the car to move, we look at the input from the driver, looking at the steering wheel speed, times this mysterious factor that Umetsu spent 8 years figuring out. That's the work. But the speed trick is because we've got to get an output from the steering wheel system. We've got to get that through the CAN bus and into the PCM, and the PCM's got to look at what the car is doing right now, calculate what it should be doing in terms of weight transfer, figure out how it can generate that weight transfer based on the gear that it's in right now, send a signal out to the engine and get that to happen in less than 50 milliseconds. Actually, I think it's usually down in the 30 or 40 millisecond range.
Dave, how long does the torque reduction last?
If you're doing sort of a theoretically pure turn-in, mid-corner exit, which you never actually do because you're always making corrections in the middle, but in that sort of theoretical world, the whole time you're moving the wheel, it's doing a torque reduction. As you're steady state in the middle of the corner, as you slow down, it comes back almost all the way up. And then as you unwind the wheel, it restores the last little bit. Because theoretically, sort of the ideal cornering posture would happen is after we straighten out the wheel, it would actually accelerate a little. But we don't want to do that. We don't want to tell the engine to accelerate more than you told it to do that. So we kind of hold back a little bit of the torque to give that back, right?
Reducing the torque of the inside wheel.
It's reducing the torque of the engine. It's not rotating the car like a torque vectoring system. It's simply doing a weight transfer onto the front tires and making the front tires more effective. So it's not actually changing the vehicle dynamics at all. It's making them more consistent. If you're driving downhill off throttle, it behaves just like this already. So what we're doing is we're making the car always have the same kind of precise, direct turn-in response that you had going downhill. If you really start paying attention, the car doesn't respond, the steering response isn't as good going uphill as it is going downhill in a normal car, in any car.
Is this programmed differently, or does it behave differently between front-wheel drive cars and all-wheel drive cars? I mean, how does the all-wheel drive?
There's fine-tuning involved for every car based on the tires we have, based on the center of gravity. Drive wheel does have some influence over it, but it does work in front-wheel drive, all-wheel drive, rear-wheel drive, right? Because basically, all it is a reduction in G and a little bit of weight transfer. But each car we have to tune the system uniquely to that car, right? And normally when we put this in, since we're tuning it for that car, we actually retune the suspension, retune the steering, and tune this all together to work harmoniously together. The reason we used the Mazda 6 for this demonstration, this is the only car where just putting it in, it worked perfectly with the suspension and steering we already had. So that's the one where we can push the button and say, this is the 2017 model, this is the 2016 model. And so what you drove, both sides of with and without, were accurate. Whereas we're going to bring this out in the Mazda 3 shortly after the Mazda 6. I don't know exactly when, depends on the boats, but that car we're also tuning the steering and suspension differently. So we couldn't just push a button and say this is how it's going to be.
So it's just Mazda 6 for 2017?
No, we'll also launch Mazda 3. It's just the 6 boat shows up before the 3 boat, so
okay.
It's technically launching first.
So, but just those two cars, that's it? Or is it
Those are the first 2 cars. We are planning to roll this out across the line, but because it's tuned for each car, we can't just push a button and throw it in every car. Even
Model year 2017 is 63.
yeah,
Yeah, that was.
MX-5 with all
we're working on that. So it's not.
Yes, it's just
Yeah, we just don't know timing. So yeah, we get vague with the timing. There's still some debate because it does behave a little bit differently, not because it's rear-wheel drive, but because of the specific geometry in the rear of that car. We're trying to get this diagonal roll posture, and there's a lot of anti-lift geometry in the back of that, so it pulls down the rear a little bit. And so there's still some debate over whether it's doing what we want it to do. It might take more tuning. It might take longer to sort it out in that car.
Sorry to clarify, it's definitely coming on the MX-5, it's just a matter of when, or you're not sure whether it's even coming at all?
I would say it's safer to say I'm not sure yet because we haven't had the solution yet, but I'm pretty sure it will.
You talk about like how you said it's a small reduction in torque. I mean, how small? Obviously it varies, but
yeah, I'm not sure in foot-pounds. I'm not sure. The extreme case, again, the acceleration G that we get is 0.05 G. 0.05 G in like an extreme lane change. In the stuff you were doing here, it's probably around 0.01 G. Right. That's why you didn't feel it. Right. And at 0.05 G in that extreme lane change, the amount of extra load we're putting on the front tires is like 10 pounds a tire. It's very small. So out there, it's like 2 pounds a tire. It's a very, very small change in the load of the tire to make a noticeable difference. To sort of a visual illustration of what it's doing. The blue line is sort of your typical steering response. The initial response is you turn the wheel, not much happens, and then it'll sort of pick up and catch up, which is why if you're sitting in the back seat of the car when we're turning the GVC on and off, you notice the lateral jerk is very smooth, and with it off, it tends to be spikier, because what happens is the driver starts to turn in and doesn't do what they want, and they speed up, and then they hit that steeper part of the curve just as they're throwing a faster input in, and they start throwing the passenger around. So ultimately, you actually end up, I push the button. You actually end up with less lock in the steering in the same corner, because you've got more response at the very beginning. You don't end up turning as far. But it's not actually changing the steering ratio. It's just changing your line through the corner to be more precisely what you were looking for. Yeah.
So you don't have that many variables inside the engine to do that torque reduction. What are you doing?
The fastest thing is to retard the ignition timing. So it's generally pulling timing. I think there might be some instances where it does something else, because basically the way that PCM is structured, if I understand correctly, and if I don't, a powertrain guy in the back is going to start yelling, and we'll know. But we've got sort of a torque request algorithm running in there, and we say we want this much less torque, and it figures out how to do it. So that's why I think it's timing, but sometimes that algorithm might come up with a different solution. The thing the area that this is affecting is just turn in, but the fact is turn in is really the most important part of the way the car handles. A variety of reasons. One, if you go all the way back to the beginning to Hashira Yorokobi, and we're trying to make people feel the joy of driving without feeling any of that fear of the fact that they're going faster than they evolved to go. That moment when you turn in is that first moment of uncertainty. You know what the car's doing when you're going straight. When you're in the middle of the corner and you have all this feedback, you know how it's going around the corner. But right when you turn that wheel, you're not exactly sure when it's going to turn in. And you process this uncertainty subconsciously. You're not going into every corner going, oh my God, I don't know what to do. But somewhere back in your brain, that's happening. And so if we can make that turn in precise, that is going to really isolate us against the most common place where we lose our confidence. The other thing is that, and this is more true the faster you're driving and the closer to the limit you are, any mistake you make at turn in resonates through the whole corner. You miss the line that you're trying to drive, and you spend the rest of the corner trying to get back on the line or trying to come up with another line that's going to work. So you get the corner right at the beginning, and you're going to be able to get it right all the way through. The other thing is that when we say turn in, we mean anytime you're making additional steering input. We're just looking at steering input speed. So it doesn't have to be just at the beginning of the corner. If you're in the middle of a corner and you make a correction, it also does that same weight transfer, and it makes every one of those adjustments work right. And so every correction you make works. So this means even when you're going straight down the freeway, you don't go straight down the freeway with your hands off the wheel. You're constantly making little corrections that you don't consciously pay attention to. And when those corrections work right, that little subconscious feedback loop between you and the car is shortened. And you just make one little correction and you're back there. So what you actually see when we have the system off, we're doing this down the freeway, and we turn it on, you just smooth right out. And that's mostly of what I just said. The other interesting point is that if the bumpier, more uneven the surface is, the more we notice a difference, and that's simply because those are forcing more corrections. It's moving the car around, and you're having to correct for it. So then, when you turn it off, you really notice all of the stuff you're doing. The other point before we get to the videos that I wanted to make on this is that the effect is really on the driver more than it is on the car. If we have steering robots we use for development where you have this thing hooked to the steering and it'll make exactly the same input, and so you can compare vehicle response with no variables, right? If we put the steering robot in the car and it does this input, it does change the vehicle response, but very, very, very slightly. If we put a human driver in the car and have them do the same maneuver, the difference is much bigger. And the reason is because the human is responding to the way the car behaves. And so they make the robot goes into a corner and it just goes this much input. The human goes into the corner and they go, I want to go on that line. They make this much input, like that wasn't it. And they make more, and like, oh, that's too much. And then they back off. And so the human is responding to the car. This is again because we focus on that relationship rather than just what the vehicle is doing itself. That you discover things that if you tune for the robots, this isn't going to show up as a useful thing. But if you tune for the people, you end up with a much more effective system. So you felt how it feels in the car. It's mostly a sensory thing, so it's very hard for us to demonstrate that. We put some cameras in there to try to see if it would show up, but usually when people are kind of looking for it, they don't drive A to B closely enough for any of that stuff to show up. But we did take some videos ourselves of guys driving A to B much more closely to kind of try to illustrate what it's doing. This is just simple straight ahead Autobahn driving like I was talking about. If you look closely at the steering on the right without all those little corrections I was talking about, this is something that doesn't seem like a big deal until you do a 4-hour road trip, and then that's actually a surprising amount of fatigue after on a long drive. And this, combating that fatigue is why most companies will go and make their steering looser and sloppier and less responsive, so that that way the car doesn't feel as nervous. Well, we're kind of going exactly the opposite way. We want to reduce that fatigue by making the car more responsive, because it's actually easier on your brain to deal with that than to chase an unresponsive steering. Like I said, it's more effective in the snow. Every one of those little corrections you make in the snow has less effect. And so you're having to make bigger corrections and bigger adjustments. You don't have as much feedback through the wheel. And that little bit of weight transfer makes a really big difference on a slippery surface. So you can see there's so much less input involved when you have that response improvement. It's hard to watch 4 videos at once, but Umetsu here is going to go around this snowy corner. Look at the steering angle on the top with GVC and on the bottom. About halfway through the corner, this car really starts to understeer, and he has to throw a bunch more steering lock into the bottom. Again, everything gets a lot more dramatic on the snow. And this is why, I'll play it again. This is why rally drivers left foot brake, because it makes such a difference. The weight transfer makes such a difference that you can't even make the car work if you're not doing it. Here's basically the same thing from the outside of the car, and this will replay and show both of them. But if you watch the front tire, this is without. See how much more the front tire is turned. You can also see when you overlay them next to each other the difference in the angle of the car. How the bottom car is pointed more toward the outside of the corner because it's understeering so much. So this is why you end up with so much more steering angle when you don't have this, because you're battling that understeer a lot more. This is another interesting example showing how the effect is really on the human more than the car. At the very end of that corner, when he's straightening back out, on the one without GVC, you notice the tail overshoots a little bit, and it doesn't with GVC. That is actually the side effect of what the driver's doing. The driver doesn't get enough response, so they put in a bunch more steering lock, and then when the car finally responds, they've got too much steering in there, and that's where the overshoot comes from. So we're getting rid of that overshoot, not with stability control, with pulling the tail back in, but just by preventing that bad input in the first place. If snow is more illustrative than pavement, ice is more than snow. So you can see how much it's slipping around on the bottom. It's actually to the point where the stability control kicked in, and that's why they went different speeds at the end, because without GVC, the stability control had to come in. See, it's all a bunch of slow motion stuff, but there's lots of big corrections going on there, again, because the driver wasn't getting the response when was overdriving the car. This is really hard to see. You can see a little bit on dry pavement. The stuff goes by so fast. But watch the end of the corner a little bit, and also watch the roll motion and how sort of abruptly the car without GVC sort of slams onto its bump stops, and it's a little bit smoother with GVC. We'll do a dry lane change out there where you can feel it much more easily than you can see it. I think the most of the time this lane change is a speed test, where to see how fast you can get through the lane change, and that car actually goes 5 kilometers per hour faster with GVC than without. So And finally, since we like our modeling agency there in Miyoshi, they actually had the model from North Carolina living in Miyoshi for some reason. This is, obviously the outside's only one shot, but inside, those two corners are same car, same speed, with and without. The reason she gets thrown out of the seat without GVC is right back to what happens at that corner when the driver turns in, it doesn't do what they expect, they speed up. And so the lateral, let me get back there and show it again. The lateral jerk spikes, and it's unexpected. It's just like we were seeing that spike in the neck muscle on the Mazda 5. That unexpected surge, she wasn't ready for it. She got thrown up out of the seat. And then because she's a professional, she just kept smiling and doing her thing. To your point about whether it's sending different torque to different axles, this is nothing at all like torque vectoring. Torque vectoring, the only thing they have in common is they both use the word vector, and the guys that developed this system are quite adamant that theirs is actually moving the G vector, and torque vectoring is not doing anything like that. Torque vectoring accurately is called active yaw control. Mitsubishi used that word first, and then nobody else could use it, so, or wanted to use it, or I don't know exactly how that works, but nobody ever wants to use the same name for the same thing. It's really annoying. So, active yaw control is actively throwing a yaw moment in by driving one tire at a different speed than the other tire and steering it like a tank on top of the steering like a car that you've got. And the reason that we don't do that is that's not a natural cornering motion. If you're walking along and somebody grabs your shoulders and twists like that, that feels really weird. That whole effort that we put into coordinating the yaw motion and the cornering G, as soon as active yaw control comes in, that goes out the window. Active yaw control can expand the performance envelope, but generally only out at the limits. Like when you get to the point where the car starts understeering, active yaw control can kind of throw in more rotation and get a little bit more cornering out of it without killing the front tires. But it doesn't work in sort of normal driving. It's only in sort of extreme maneuvers that it does something. Yeah.
Does this plug in neatly with predictive all-wheel drive?
It works. It's parallel. I mean, they're both trying to manage traction, but through completely different mechanisms.
Interactions between the two that you didn't expect.
But no. All-wheel drive is no surprise, right, Umetsu-san? There's no unexpected interaction between all-wheel drive system and the GVC, right? It works exactly the same with all-wheel drive.
Yes, we have same influence for the FWD and the AWD people. And the GVC is just improving based on the basic performance of the chassis and the tires. So we can say with GVC we can improve we can maximize the performance of the chassis. It's using the weight transfer, road transfer, optimize the road transfer.
The fact that both of them end up with benefits of making the car turn more consistently and precisely in the snow it's more a result of the fact that our goals of the way the vehicle is supposed to behave are the same. All the different groups are working toward the same goals, and all the results of those are much easier to see in the snow. So we keep showing snow videos. And they're much easier to feel in the snow too. I mean, because when you get to the limit, and it's a very slow, soft limit like you get in the snow, you have time to sense everything, and everything sort of becomes very clear. But ultimately, these are all sort of different elements working toward that same goal of Jinbai-Tai. Right.
And Dave, is it safe to assume that adding this feature resulted in zero bill of materials?
Software only. Yeah.
So a lot of R&D to figure it out.
A lot of R&D to figure it out, but once it's in there, it doesn't add any cost, doesn't add any weight.
You had to have the fancier computer, but you got for other reasons.
But because the SkyActiv engines takes such intense control that was there anyway.
Right.
There were, I think, a couple of little tweaks in the details of those communication channels to get them to do to process this particular request faster than they were before, but it wasn't significant changes.
So can current cars be updated?
No. there's constantly other changes. We were talking about this yesterday. There's constantly other changes going on in the PCM, and in parallel with the GVC changes, some of the other logic has changed. So if you could try to put this programming into the older car, but then it wouldn't run. GVC would be great, but it wouldn't run. So theoretically, you should be able to, especially on the 6, where it's all the same setup, but because of all this sort of detail stuff going on underneath, it won't actually work. Just in defense of the name, or explanation of the name, G-vectoring is referring to a vector is just the value and a direction. So the G-vector is the amount of G-force and what direction it's pointing. And your typical cornering force is just a G-vectoring pointing toward the inside of the corner. And what this system is doing is trying to give you that what we think is a natural cornering posture, where the G-vector goes forward a little bit and then rotates around, then points to the back as you power out of the corner. And so we're actually moving the G-vector with the G-vectoring control system. So just like we think Miller cycle is a better name for Atkinson cycles, we're going to stick to what we think is right, even when nobody else understands us.
Never require a supercharger.
No, it doesn't. A Miller cycle is an Atkinson cycle that's done with valve timing. That whole supercharger thing was because the guys who launched the Millennia didn't understand that. Again, just to drive home the point of the difference between G-vectoring and active yaw control, the G-vectoring is helping in completely ordinary driving straight down the road, where active yaw control doesn't do anything. Some active yaw control systems will help in a quick lane change, but mostly it's sort of the big limit handling stuff that we all like to go out and do that speaks to those of us in the room, but not to the rest of the customers. So most people actually will never even feel any of the benefit from a torque vectoring system. A lot of the times it expands the performance envelope in ways that require you to drive specially to extract it. And you narrow down the number of people that actually are going to drive that hard, and then drive it down even more to the number of people who can figure out what to do with active yaw control to get a benefit from it. And those of us who are in that tiny little sliver really think it's fun. But the rest of the people that are buying it are just paying for our fun, really. So that's sort of the key difference. Also, you notice that our little button had 2 different names on it, which is confusing: Sky Active Vehicle Dynamics and G-vectoring control. Sky Active Vehicle Dynamics is a category name for technologies of this type, where we're sort of holistically taking different parts of the car and making them work together to accomplish something new. Right now, that category has one thing in it called G-vectoring, so the names are sort of interchangeable at the moment, but when we have some other things to go into that category, it'll make more sense that we gave it 2 names. That's all the pre-programmed yapping that I have built in. So, yes,
an option of standard.
It's going to be standard. It's going to be with every car that it rolls out in, because as we roll out into everything, when it comes out, it will be standard. There'll be no off button. There'll be no indicator light. There'll be nothing. The car will just steer better. Because there really isn't any time where you'd rather have the steering be sloppier and less responsive and less consistent.
How does it play with semi-autonomous, like lane keep assist and stuff like that, where sometimes it'll jerk you back in? I mean, can this make that a little smoother and more organic?
Well, no, because what it's doing is really working on the feedback loop with the driver. And unfortunately, those lane keep assist systems are really interfering with that feedback loop and confusing it, which is why the one car that so far that we have lane keep assist on has a much softer, more subtle, less of a jerk back into the lane, and more of a strong suggestion back into the lane. But yeah, this is really completely the opposite direction of autonomous driving. Rather than focusing on what the car is going to do by itself, we're focusing on what will make the car respond to the driver better. Hopefully everybody felt it and got what we were trying to do and tolerated the long, slow process of introducing it to you. I think you'll understand that if we'd done it the other way and just thrown you in the car and said, feel this, you would have been, feel what, right? So I think that was probably necessary. As far as I'm concerned, I think the takeaway from this is why we actually bothered with something like this. That's very subtle, but I think very important. It's not something you can very easily put on a spec sheet and charge $1,000 for. which would maybe stop it from getting developed at an ordinary company. But that's why we started this whole discussion off with philosophy and what we're thinking about and why we do stuff like this, because ultimately this is taking a Mazda and making it just that much more a Mazda, and we firmly believe that matters, and making a car drive right matters, and that ultimately it's going to be a successful strategy.